Atoms, ions, and molecules are really, really small. So when we want to work with them in the macro scale world, it helps for us to be able to count a lot of pieces by using a grouping unit. Let's take a look back at balanced chemical equation. So a balanced chemical equation is a concise description of the chemical reaction taking place. So let's start with a simple chemical reaction. Two hydrogen molecules react with one oxygen molecule to give two water molecules. So that's how we've been talking about these balanced reactions. But how do we move that into the macro scale world? How do we move that into quantities that we can actually measure in real life? So we can think about that. How many H2 units exactly are in 1 gram of hydrogen gas? Or how many oxygen units are in 1 gram of oxygen gas? And we can make some predictions. We can look at our elements on the periodic table, but how do we make that connection between micro and macro? Well, as I said, we need a grouping unit. So grouping units in general are units that allow us to refer to a larger number of things using a smaller number. So one way we can think about them is most conversion factors, we can think of those as grouping units. So if I'm going for a walk, I probably would never tell somebody, yeah, I'm going to go for a walk and it's going to be 236,966.4 inches, because inches is a really small unit for what I'm describing. I can group that into a larger grouping unit, feet. There are 12 inches in a foot, and I could say that, well, I'm going to go for a 19,747.2 foot walk. But again, that's a pretty big number and a little bit clumsy to deal with. If we convert that up and group that into now miles, there are 5,280 feet in a mile, so my walk is going to be 3.74 miles. There are lots of grouping units that we use all the time, and some grouping units are very rigidly defined. Some grouping units are a little bit more varied. So something like a case of soda. A case of soda used to refer to a 24 pack. But now 12 packs are much more common. So depending how you define a case, that could vary a little bit. A gross of self-sealing stem bolts. Gross is a dozen. That's a very rigidly defined quantity. It's 144. A deck of cards. If we're talking about a standard deck of cards, that's 52 cards. If we're talking about another type of deck of cards, it might be different. But that grouping unit is a deck. So we've got a lot of grouping units that we use pretty comfortably in daily life. Now we're going to look at the chemistry grouping unit. And that grouping unit is called the mole. So 1 mole is equal to 6.022140076 times 10 to the 23rd pieces. And at this point, that's an exactly defined number. Now it's exactly defined with 1, 2, 3, 4, 5, 6, 7, 8, 9 sig figs. So it's a pretty precise, exactly defined number. But if we write that out as a number, let's put all these zeros in. That is, and this is 6.022 times 10 to the 23rd, defined exactly to that 6. So this is a huge number. To put that into a little context, I mean, first of all, this constant is often referred to as Avogadro's number. Amedeo Avogadro was an Italian chemist 200 years ago, approximately, who worked on this idea of weighing out elements to count their pieces. So if we think about this, a mole, it's a lot of pieces. But again, atoms and molecules are tiny. So a mole of water is 18 milliliters. 18 milliliters isn't very big. A standard can of soda is 300, 400 milliliters, something like that. So that's pretty small. Those water molecules have to be pretty small to fit 6.022 times 10 to the 23rd of them in 18 milliliters. To use some normal things that we might be accustomed to, if you took a mole of rice grains and you stacked them or you laid them side by side, they would go around the Earth about 45 billion times. That's a lot of rice. Another, maybe more practical one that you can think of, a basketball, right? You know how big a basketball is. If we had a mole of basketballs, the volume of a mole of basketballs would be about 5 times the volume of the Earth. So, A mole is a lot of pieces. B, atoms, ions, and molecules are really, really tiny pieces. Now, one of the interesting things here, 6.022 times 10 to the 23rd seems like kind of a random number, but it's not a random number because one of the purposes of the mole is to allow us to connect the macroscopic world and the microscopic world. So if we're measuring mass in the microscopic world, we would usually think about that in terms of AMU, atomic mass units. On the macroscopic world, we don't use AMU because it's too small a unit. We need a bigger unit, so we measure grams, for example. So what if I take, so here, this is back from chapter 1, chapter 2, 1 AMU is 1.661 times 10 to the minus 24th grams. Tiny, tiny unit. And again, at the time, that may have seemed like kind of an arbitrary number. But what if I have 1 mole of atomic mass units? If I have 1 mole of atomic mass units, 1.661 times 10 to the minus 24th times 1 mole of particles per, or number of particles per mole, what do we get? 6.022 times 10 to the 23rd? Go ahead, plug that in your calculator. It's 1. So the mole is a way for us, in a mass sense, of relating the macro and the micro worlds to each other. And that comes up on the periodic table as well, right? So we've got our standard periodic table here. And when we talked about this, we said, take, for example, beryllium. An average beryllium atom has a mass of 9.012 AMU. But remember, moles relate AMUs and grams. So we could also say that a mole of beryllium atoms would have a mass of 9.012 grams. That's one of the reasons the units aren't included on periodic tables, because depending whether you're talking about the macro world or the micro world, we can use this number to describe either AMUs or grams. How do we use that practically? Well, the place we're going to use this most often is when we're looking at things like formula mass, because formula mass is something that we already talked about in the micro world, right? So what's the formula mass for phosphorus trichloride? Phosphorus trichloride, PCl3, phosphorus trichloride. So I've got 30.974. This is from the periodic table on the previous slide. AMU, that's the mass of phosphorus. I've got 3 chlorides at 35.453 AMU each. Multiply, add those together, you get 137.333 AMU. That is the average mass of a PCl3 molecule. But what if I'm on the macro scale? What is the mass of 1 mole of phosphorus trichloride? Again, PCl3. Well, now I'm going to use those numbers off the periodic table with their macro scale units, grams per mole. So phosphorus has a mass of 30.974 grams per mole. I've got 1 mole of phosphorus here. 1 mole of phosphorus and phosphorus trichloride. Chlorine, there are 3 moles of chlorine in every mole of phosphorus trichloride. So I've got 3 times 35.453 grams per mole. So my formula mass, my molar mass in this case, because it's per mole, is 137.33 grams per mole. And those are the exact same number. They're the same numerical answer, but they have different units. This is one of the reasons why it's important for us to always include units on every number that we report. So we're going to dig into this a lot more in a lot different ways, but that is just a brief little look at the mole as a grouping unit and some of the ways we use it. Practice a lot of these. We're going to have lots of opportunities for that, and I'll see you next time.